So hi, I'm Derek Kozel. I work with Edis, and so I spend a lot of time with USRPs and answering people's questions. Where usually it's, my signal doesn't look like I expect it to. And one of the most frequent things that people trip over is synchronization. And so I'll be talking about synchronization, and specifically frequency, time, and phase synchronization. And GNU Radio has a lot of DSP blocks that do various forms of synchronization, and I'm not going to be talking about them. I'm actually going to be talking about the physical synchronization of the hardware. And so this varies from hardware platform to platform. Even within in Edis, it varies a bit in what the hardware is actually capable of. And I'll be pointing out a few of the spots where these differences come into play. And so that's going to be my overview of the problem and why this ends up being fairly tricky to implement. And so there's that variation. So jumping right in, probably everyone here is familiar with this, but we generate a baseband signal and we mix it up to a higher frequency, or the opposite when you're doing receiving. So you have this carrier on the transmitter and you have a carrier on the receiver, and this has frequency and phase information. And so we're going to start off by talking about the frequency information. And again, this is going to be probably pretty obvious, but people do trip up on this. So how is the carrier actually generated? What ends up happening is you have an optional external reference or an internal reference, some oscillator that's running at some frequency, and it's never ever at your, well, almost never, at your carrier frequency. You have something like a 40 megahertz crystal, and then that has to get multiplied up to your actual RF frequency. And so usually this is done with a fractional N based synthesizer, and this is actually what's run into your mixer. And so you have the signal coming from your antenna, run through the mixer, into the ADC, with lots of other details in the middle that we don't care about. So what does a fractional N synthesizer actually look like? It has your input reference. I was saying 40 megahertz. It varies hardware to hardware. There's an optional input divider. Then you have a phase detector. And fundamentally what's going on is that they're comparing, this compares the phase of your reference signal to the phase of your output signal that's been divided sometimes. So, say we put in for easy numbers, 10 at the reference, we have no input divider, then we have a loop filter, which just helps smooth things out a bit, and your VCO runs at some rate, and your fractional divider is 10. So we're going to multiply the signal by 10. So we're going to have 100 megahertz at the output. And so it goes through the divider. Now we have two 10 megahertz signals, and it just checks to see that they're actually phase locked. And this is how we get the disciplining of this higher frequency VCO. Now, unfortunately, what this introduces, or what this means, is that the accuracy of your reference is what actually gets transferred onto the VCO within the passband of the loop filter. So if your input is really terrible, your system's just not going to work very well at all. But if you have an extremely good reference, then you're able to transfer a lot of that accuracy onto the VCO. And what's also interesting is that, I presented it 2 slides ago, that you have the synthesizer and it's driving a mixer. Now, we're talking about SDRs. So you also have the ADCs and the DACs. And these accept sample clocks. And a lot of the time, that sample clock has to be driven externally. And so we drive it off of the same internal reference. And maybe we have to mix it up, multiply it up, multiply it down, change the rate so that we get exactly what we desire. But it's still going to be based off of the accuracy of that internal reference or how it's disciplined. So that goes into the ADC. And if there's a timing difference, if you have 2 different SDRs that aren't sharing any sort of external reference, then you might end up with things still being perfectly on frequency. It's unlikely, but offset by a little bit. And so you'll end up with a time shift or a phase shift, depending on what your signal looks like or how your perspective. And then if you have jitter on that reference, which you'll always have a little bit, that ends up increasing your phase noise. So it's one of the fun things, SDR. You can't just look at the performance of your mixers, the performance of the RF signal into the mixers. Your ADCs are also contributing to this, and your DACs. And so this is one of those instances where you can really improve things by supplying an external reference or just making sure that your internal is actually quite stable. So this is an overview of kind of the most common references that are available. Most boards will have either a crystal or a TCX, well, most of them will have a TCXO on board because those are pretty cheap these days. And so we measure these in fractional frequency error as one of the key metrics, and that's just how accurate is your frequency actually compared to what your desired frequency is. And so TCXO is nice. We get 10 to the negative 6, which means that we have 1 hertz error at 1 megahertz. And that's nice if you're doing very low frequency signals. But once you start getting up into the 2.4, 5 gigahertz, or one of my hobbies is amateur radio, and I'm working on 10 gig, 24 gig systems using SDRs. And if you have 10 to the negative 6 as your frequency accuracy, you could be wandering all over the band. Well, wandering would be stability, but you could be located hundreds of kilohertz off. So you go to OCXOs and you're doing a bit better, 2 orders of magnitude, and these are all approximate numbers. You can get nice, you can get worse. Then you get up to rubidiums. Now you're into atomic clocks. You're getting really, really nice both stability and accuracy. And then if anyone has a cesium clock, I'd love to see it someday. But you can get truly phenomenal accuracy with that. And people go even farther. But we're unlikely to have that available. So that covers frequency synchronization. And that's the basic principle there is just if you supply an external reference, then you can have that shared between different SDRs, and so they'll all be at the same frequency, and you're translating that accuracy onto all the radios. And if they drift, they'll drift together because they're all sharing that same frequency reference. Time. Many applications require high-precision timestamps, whether that's doing radio astronomy and you want to know exactly when your sample acquisition starts, or you're doing TDMA protocol or something like that where you really want to know what nanosecond this started or what millisecond even. You have to take into consideration where are you actually recording the time that these samples were acquired. Because if you're going and recording it on the host and you're saying, oh, my CPU's clock says that it happened at this time UTC, your PC's clock isn't all that great. If you're using NTP, you might be getting down to into the microseconds resolution, but that's really optimistic. And you're being degraded by the time that it takes the samples from the acquisition at the ADC to go through your processing system, whether that's an FPGA or just directly onto some transport bus, into your kernel or your OS subsystem, up and actually surface into your application. So it's nice if you can do that timestamping actually on the radio. And a number of radios do implement this in the FPGA where they have a counter and it actually tags metadata onto the samples. And so it can be useful or essential to have the time available on the device. And I'll cover another point in the phase discussion where you really want to be able to have things occur on the radio at a precise moment. And especially if you have multiple radios, you want them to have a shared time base there. You want to be able to run exactly the same commands across these radios at the same moment. So how do these radios actually find out what the time is? How do they establish this common time base? And the most common answer is you supply some external clocking edge, usually a 1 pulse per second because those are fairly ubiquitous. Most GPSDOs will output them. Some test equipment has them. And this is an Edis product, but you can get generic, you can get many other clock distribution amplifiers. And so they'll accept a 1 pulse per second in, or they'll have a GPSDO on board, and they'll fan this out. And they'll fan it out very carefully so that all of the rising edges at the SMA connectors are actually occurring at the same moment. And so the trick there is you have to have equal length cabling so that these rising edges are arriving at your SDR at the same moment. And this has kind of been a very staple thing in the RF world for a long time. So it's probably not a new concept to most people, but it's interesting seeing the number of applications where this is really a great answer if you have everything on a bench. particularly if you're doing beamforming or other applications where you need this shared time and frequency base. And so this particular one also has the 10 megahertz reference that can be distributed to all the radios at the same time. And so GPS DOs, here's where you have, if you have multiple SDRs at multiple locations and you want them to have this shared time base, you can use GPS. I threw in this graphic here. Until 2000, May of 2000, the US government had selective availability, and so the general public didn't have access to the high precision data. And so you can actually see the decrease in uncertainty when that was turned off in this plot, which I always enjoy. But still, unless you have an extremely good GPS receiver, the rising edge of the pulse per second actually has a 10 to 50 nanosecond uncertainty usually. And that's good enough for most time synchronization. Very few applications need better than that. So it gets used very often. But if you're streaming at something like 200 megasamples per second, that's still a 2 to 10 sample timing error. So that's when some of the higher level synchronization in DSP needs to take place if you really need to hone in on an extremely precise one. But if you have the same, again, if you have the same pulse per second edge supplied to all of your SDRs at a location, they'll still have this error in reference to the global time scale, but on their local time scale, they'll all actually be synchronized. And so the last topic is phase synchronization. And remember, we're talking about physical phase synchronization. So this isn't directly related to like demodulating coherent signals, or phase shift keying, where you need to demodulate using a carrier that matches the carrier that's phase synchronized with the carrier of the transmitter. This is much more for beamforming, direction finding, applications where you're doing self-cancellation to get more isolation between your transmit and receive channels. And this is what it looks like just in GNU radio in a time plot. And it looks like a timing offset. You can apply a phase, you can do a multiplication and bring those phases into line. But how do you actually measure that? Oh, sorry. So synthesizers, this is one of the places where fractional N synthesizers have a bit of an issue. Because you have that divider in the feedback loop, you introduce this ambiguity. You don't know which rising edge of the output signal, where that should be in relation to the input. And so a lot of synthesizers have begun including mechanisms to resynchronize this. But this requires that all of the synthesizers in your synchronized SDRs receive a command, or either the command to tune or an outside synchronization signal that's extremely precisely demarcated in time. And so here we can see this is the Analog Devices 4351 synthesizer, and this is a clip out of their data sheet. And so you can see that this is all internal. It's one of the synthesizers that will resynchronize itself in reference to the reference input frequency, and it settles onto the incorrect phase during the tuning, and then there's this internal sync signal, which is phase locked to the reference input, and it synchronizes down to a known phase. And so this is where timed commands come in. If the FPGA or the SDR has a concept of time on board that can be synchronized via the 1 PPS or another mechanism, then that's how you're able to have this command go out to all the synthesizers simultaneously. And if you're not frequency synchronized between these units, then there's no point even trying to phase synchronize, because your phases will be sliding relative to each other if you have a small frequency error, or they'll just look completely wrong if you're off by kilohertz or megahertz. So these phase offsets. So if you've gone through all these steps, you have frequency references, so they're all very accurate in frequency. You have a shared time reference, either through GPS or 1 pulse per second. And you take the work into the synthesizers, and you get the fractional N synthesizers to resync. You take your measurement, and all of a sudden you're like, there's still a 20-degree phase offset between these channels, or a 10-degree. Why is this occurring? And it's because these synthesizers are settling, the synthesizers should hopefully all settle to the same phase offset relative to the reference signal. But the cable lengths could be long. There could be differences in layout in the physical traces on the board. And remember, at high frequencies, 3, 4 gigahertz, your wavelengths are measured in centimeters. So if you have just a few millimeters extra, you could see several degrees of phase shift between your channels. But the nice thing is, you've gone through all these steps. These should be consistent offsets. So you can use GNU Radio very trivially to measure this. If you multiply one signal by the complex conjugate of the other, and then do a complex to arg function, you'll get out the phase offset between the two channels in radians. And then you can do just a multiply by e to the j with that radian value and correct for that phase offset in software. And so, yeah, it's quite simple here. But you can see here, this is a USRP. It's synchronizing off of a PPS. It has an external clock source, an external time source, and so it's all fully synchronized between these two channels. And so, yeah, so different applications require different levels of synchronization. If you're just trying to do FM broadcast, you don't need phase synchronization. You probably don't need time synchronization. You just need some level of frequency synchronization so that you're not completely listening to the wrong area of spectrum. But if you're doing beamforming, you're going to have to go through all the steps and make sure that everything is very stable and synchronized. Yeah, the shared physical references are convenient, but you can still get them wrong if you have different length cables, you have the amplitudes wrong and stuff like that. And GNU Radio has a variety of the DSB-based blocks. If you're just going to GRC and look up synchronization, there's a few there that will allow you to track carrier frequency drifts and stuff like that. But I haven't talked about those. Does anyone have any questions in the last minute or two before I'm done?
Oh, here, Michael, you can use mine.
So I'm going to ask this question in the terms of when I was probably an undergraduate and before I got smacked around by reality. You said, like, coming out of the octo clock that, all those cables, if they were the same length, then, things could match up. Yeah, but, like, how important can the cable length really be?
So the cable length, it depends on the frequency that you're operating at. Given that it's a 10 megahertz signal coming out of the 10 megahertz references, velocity factor of like 2/3, something more than that, but make the math easy. It's not going to make a huge amount of difference, especially given that the phase offsets, you're not going to see that many degrees, and you're still going to have these constant phase offsets that you're probably going to be calibrating out anyways. It's not going to affect the frequency synchronization. But if you have the pulse per second edge, and you're off by even just a little bit, I forget what I calculated out as, but these are extremely sharp rising edges, and so you don't want those shifted by even a single clock cycle in the FPGA. So it depends on how fast your SDR is actually running and how it's synchronizing. It's not, if you're a centimeter off, you're probably fine, unless you're doing something extremely precise. But if your cable is 50% longer, then you probably have a problem. Or an appreciable fraction of wavelengths is the more accurate, probably, except for the PPS.
Any other questions? No? All right, let's thank our speaker. Thank you, Derek. Thanks, dude.